Welcome to our quantum deep dive. Today we're plunging into a technology that really feels like a paradigm shift. Quantum radar.
Yeah, it's fascinating stuff. It uses some of the, strangest rules of the universe to potentially see things classical radar just can't.
And guiding us through this is material from the essay Quantum Radar, Die Zukunft der Radartechnologie by Jörg Oschneppat. Our mission here is to, break down what quantum radar actually is, how it taps into quantum mechanics, and really why it could be such a massive game changer across so many fields.
Definitely. And I think to really appreciate the quantum leap, it helps to start with where we are now, classical radar.
Right, the standard stuff. The basic idea has been around forever, hasn't it?
Pretty much. You send out electromagnetic waves, radio, microwaves, that sort of thing, and you just wait for them to bounce off something, an object.
And the time it takes tells you how far away it is. There's that formula, right? Distance is speed of light times time divided by 2.
Exactly, because it's got to go out and come back.
Yeah.
Simple, effective, it works.
But it has limits. Big ones.
Huge ones, especially nowadays.
Yeah, like stealth technology. Designed specifically to, not bounce those waves back.
Right, they absorb or deflect them. Makes detection really, really difficult.
And then there's just noise. Weather, other electronic signals, general clutter.
Oh, yeah. It can totally swamp the signal you're looking for. It's like trying to hear a tiny whisper in a hurricane.
So classical radar struggles with faint signals and things designed to hide.
And that's exactly where quantum mechanics comes in. It offers a totally different approach.
Okay, so instead of just brute force signal strength,
it uses the inherent, weirdness of the quantum world. Things like superposition and entanglement.
All right, let's tackle those key quantum ideas. First up, superposition. What's the gist?
Well, in the quantum world, a particle isn't forced into just one state, like on or off, 0 or 1. Before you measure it, it can actually be in a combination of possibilities, all at the same time.
Like being both heads and tails at once before the coin lands.
Sort of, yeah. Think of a quantum bit, a qubit. A normal computer bit is either 0 or 1. A qubit can be a mix of both 0 and 1 simultaneously.
The source mentions some math notation for that.
It does, yeah, showing the probabilities add up. But the core idea is that potential for multiple states existing together. It's fundamental.
Okay, multiple states at once.
I got it.
Now, the next one sounds absolutely crucial for quantum radar. Entanglement.
Entanglement. This is where it gets really interesting and, frankly, a bit mind-bending.
But that's what quantum mechanics does best,
That's
right?
pretty much. So entanglement is this incredibly deep connection between 2 or more particles. They become linked.
Linked how?
Linked so that they essentially share the same fate, the same quantum state, no matter how far apart they get. If you measure something about one particle, you instantly know the corresponding property of the other one.
Instantly. Even miles apart.
Instantly. It's not communication in the normal sense, it's a shared existence. The source gives examples like entangled photons where their polarizations are perfectly correlated. You measure one, you know the other.
Einstein's spooky action at a distance.
That's the one. And it's absolutely real and vital for this technology.
Okay, and there's one more. Quantum coherence. What's that about?
Coherence is basically the property that allows these quantum effects like superposition and entanglement to persist. It's the quantumness staying intact.
Keeping its wave-like nature.
Exactly. But it's incredibly fragile. The opposite is decoherence.
The enemy.
The big enemy, yeah. Any interaction with the environment, heat, light, vibrations, anything can destroy that coherence, collapse the quantum state back into a classical one, and break the entanglement.
So maintaining coherence is a huge challenge.
A central challenge. Without it, the quantum advantage disappears.
Okay, so summing up the quantum bits, we have superposition, multiple states, entanglement, spooky connection, and coherence, keeping the quantumness alive.
That's the toolkit.
And in quantum radar, we're using entangled photons as our quantum bits, our qubits.
That's the most common approach, yes. Entangled photons carry the quantum information.
The source also mentioned quantum teleportation briefly.
Yeah, just in passing. It's not the main detection method right now, but the principle of transferring quantum states using entanglement might play a role down the line, maybe for relaying information about what happened to the photon out there.
Interesting. Okay, so let's put it all together. How does this quantum weirdness actually let us, detect an object?
Right, the mechanism. It starts, naturally, by creating a pair of these entangled particles, usually photons.
Okay, generate 2 linked photons.
Then you split them up. One photon, let's call it the signal photon, gets sent out into the environment. towards where you think a target might be.
And the other one?
The other one, the idler photon, its entangled twin, you keep safe and sound back in your detection system. It's your reference copy.
Okay, so one out, one stays home, but they're still linked by entanglement. What happens next?
The signal photon travels out. If it encounters an object, it interacts with it. Maybe it bounces off, maybe it gets absorbed slightly, maybe it just passes nearby and is subtly affected.
So any interaction.
Any interaction changes its quantum state, even a tiny change. The source describes this mathematically like an operation transforming its state.
And because it's entangled.
Exactly. Because it's entangled with the idler photon back home, that change to the signal photon state is instantly reflected in the correlation between the two.
Ah, so you're not just looking for a reflected pulse coming back.
Not primarily. You're comparing the state of the photon that interacted, or maybe detecting its loss, with the state of the idler photon you kept. The presence of the object reveals itself through the change or disruption in that shared quantum entanglement.
Okay, that is different. It's not about the strength of the echo. It's about seeing if that quantum link got disturbed.
That's the essence of it. And this gives it potentially massive advantages.
Like detecting stealth.
Precisely, because you're detecting the interaction itself, not just a reflection. An object designed to absorb classical radar waves might still interact with a quantum photon in a detectable way, changing its state and thus revealing itself through the entanglement.
That makes sense. And what about the noise problem that plagues classical radar?
This is another huge potential win. Because the detection relies on the specific correlation unique to that entangled pair, you can design the system to be much less sensitive to classical noise.
How so?
Well, random noise in the environment might hit the signal photon, but it won't have the specific entangled correlation with the idler photon. The system can essentially filter out anything that doesn't match that unique quantum fingerprint.
So it pulls the signal out of the noise much better.
Potentially much, much better. The source specifically mentions an improved signal-to-noise ratio. You get coherent information even when things are messy.
Wow, okay, that sounds incredibly powerful. So, why don't we have these everywhere already? What are the catches?
The catches. There are quite a few, and they're significant. The biggest are the technological hurdles.
Like keeping that entanglement alive.
Exactly. Back to decoherence. Maintaining that delicate quantum correlation over any real distance in a potentially noisy environment, it's incredibly hard.
So you need serious protection.
Absolutely. Very precise quantum optics, sophisticated shielding from vibrations, magnetic fields, stray light, and often, as the source points out, you need things to be extremely cold cryogenic temperatures to minimize thermal noise and interference.
Okay, so it's delicate. What about building the actual hardware?
Also very challenging and expensive. You need specialized sources to generate high-quality entangled photons reliably. And you need detectors that can register single photons with extremely high efficiency.
Single photons.
Yes. The source mentions things like superconducting nanowire single photon detectors, or SNSPDs. They're amazing, very efficient, but they usually need that intense cryogenic cooling.
Expensive.
Very. The source notes a detector system alone can cost hundreds of thousands of euros. So complexity and cost are major barriers right now.
Okay, so it's tough to build and operate, but assuming researchers keep making progress, where could this technology actually make a difference? What applications does Schneppat's essay highlight?
The potential is really broad. Let's start with defense and security.
The obvious one, maybe. Countering stealth.
That's a huge driver, yes. The ability to detect objects designed to be invisible to classical radar could fundamentally shift the strategic balance.
And things like missile defense.
Definitely. Better early warning for missiles, drones, especially in environments with lots of jamming or clutter, and potentially tracking their paths much more accurately.
Okay, defense makes sense. What about beyond that?
Air and space is another big area. Imagine much more precise navigation for aircraft or collision avoidance systems that work flawlessly even in thick fog or heavy air traffic.
That could improve safety significantly.
Absolutely. And in space, think about detecting faint or small objects, maybe tiny asteroids or hazardous space debris that current radar misses, or even getting finer details when mapping planets.
Okay, and then there are the civilian applications. The essay mentions those too.
Yes, and this is where it could impact everyday life, perhaps most directly. Medical imaging is a really exciting prospect.
How would that work?
The idea is potentially non-invasive imaging with much higher resolution or sensitivity than things like ultrasound or MRI, maybe detecting tiny structures like the very beginnings of a tumor or getting much clearer views inside the brain.
Wow, seeing things at a much finer scale without surgery.
That's the hope. And another area is environmental monitoring and climate research.
Like tracking pollution.
Exactly. Detecting emissions with greater precision, monitoring tiny changes in glacier thickness or sea levels, maybe observing the fine structure inside storms or tornadoes much better than we can now. Higher accuracy, finer detail.
So the potential applications are really transformative. Defense, aerospace, medicine, environment.
Across the board. But as we said, the hurdles are still there.
We cover the technical challenges, the cost, complexity, decoherence. Are there other roadblocks?
Oh, yes. The essay brings up some really important ethical and societal questions.
Like what?
Well, on the military side, if one country develops truly effective quantum radar, it creates a massive strategic advantage that could easily destabilize things, maybe trigger a new kind of arms race. There are big questions about offensive versus defensive uses.
Right, the geopolitical implications.
And then there's the surveillance aspect.
If this tech gets really good,
Yeah.
could it see through things?
That's one of the potential avenues of research, using quantum effects to potentially probe environments in ways classical methods can't. Maybe even seeing through certain barriers.
Which raises huge privacy concerns.
Huge. Imagine the potential for misuse if you could effectively see through walls or monitor people without their knowledge. How do we regulate that? It's a massive challenge for data protection and personal privacy.
So we need to think about the rules before the tech is widespread.
Absolutely. It requires serious discussion now.
Okay, given all this, the potential, the challenges, the ethics, where are we now? Is this still purely theoretical?
Not purely theoretical, but definitely still experimental. Very active research, though.
Was working on it.
Major research groups around the world. The source mentions places like the Max Planck Institute, MIT, Stanford, and also military research agencies like DARPA in the US.
And they're building prototypes.
Yes, and importantly, these prototypes have shown the basic principle works. They've demonstrated detection of small objects, sometimes in noisy conditions, using these quantum techniques. So, proof of concept is there.
What needs to happen next? What are the key breakthroughs needed?
Well, continued improvement in the core components is vital. Better ways to generate entangled photons. The source mentions things like quantum dots or photonic crystals.
More efficient sources.
Right. And better detectors, those SNSPDs becoming more sensitive, maybe easier to cool. And a big trend is integrated quantum optics.
Putting it all on a chip?
Basically, yeah. Miniaturization could eventually help with size, robustness, and maybe even cost. And alongside the engineering, we need advances in fundamental materials science. Finding better nonlinear crystals for photon generation, new superconducting materials for detectors, maybe even exploring exotic physics like topologically protected states to fight decoherence?
It really feels like this could spawn whole new industries.
No question. You can see new business models emerging in aerospace, medical technology, environmental services, maybe even linking up with quantum communications and cryptography. It's potentially disruptive.
Which loops back to the societal view.
It does. We have to weigh these incredible potential benefits, safety, health, knowledge, against the very real risks we talked about, privacy, military instability.
So public discussion is key.
Essential. We need open conversations about responsible development and regulation as this technology matures.
Okay, let's try and wrap this up. Key takeaways from this deep dive.
I'd say quantum radar is a truly revolutionary concept. It swaps classical reflections for quantum entanglement.
Right, using that spooky link between photons.
Which gives it major potential advantages, especially against stealth and in noisy, cluttered environments.
And the applications are vast: defense, space, medicine, climate.
Huge potential. But it's not just a better radar, it's a fundamentally different way of sensing, opening up possibilities we couldn't even think about before.
While acknowledging the significant hurdles, technical, physical, and especially ethical, that still need to be overcome.
Exactly. The science is progressing, but the societal questions need just as much attention.
So a final thought for you, our listener, to ponder. As we develop this incredible new power to see, how do we ensure it enhances our world without compromising our privacy or our security? How do we navigate the complex ethical and geopolitical landscape this creates?
It's something we all need to consider.
This deep dive was based on excerpts from the essay Quantenradar, Die Zukunft der Radartechnologie by Jörg Schneeppert. Thank you so much for joining us.
Goodbye.